Topic that we will be discussing today is about thermodynamic processes. In this topic, there will be 4 processes to be introduced. The more formulas you memorize for each topic, for each thermodynamic process, the easier you can solve a problem. The common issues that the students encounter in this topic is that without the table or the summarized formulas that they made for each process, they cannot answer the problem. But in this module, I will teach you how to gain confidence and be independent enough with thermodynamic processes, and then you can easy solving the problems about the process or about this topic. We will be just using a simple derivation with an application of integral calculus. So first, I would like to tackle its main definition. So a thermodynamic process, it says here that when the system undergoes change from one thermodynamic state to final state due to in properties like temperature, pressure, volume, and etc. The system is said to have undergone thermodynamic process. And the various types of thermodynamic processes are isothermal process, adiabatic or isentropic process, isochoric or isovolumic process, and then isobaric process. So first, I would like to tell you about 10 facts before we go to the derivation of for each process. So the first fact is about the change in temperature or the change or in any variable. So when we say change in temperature, this is the final temperature minus the initial temperature, or when we say the change in volume, that is the final volume minus the initial volume. So when the temperature, so in this example, when the temperature is constant, we could say that change in temperature is equals to 0. Take note that the temperature is just constant. The temperature is not equal to 0, but it is the change in temperature that is equal to 0. Because if we are going to assume, let's say we have 5 Kelvin, so 5 Kelvin is constant, so 5 Kelvin minus 5 Kelvin equals to 0. So do not be confused with the temperature and the change in temperature because it is mainly different. So the second fact is about the ideal gas equation. So it's just a recall. So we know that the PV-nRT or paborito niya, PV-mRT or paborito mo, and then this is a derived equation when there is a mass density involved. And of course, here is also a derived equation when the specific volume is involved. So fact number 3 is about ideal gas laws. So again, we have Boyle's law. This is the equation for Boyle's law, for Gay-Lussac's law, and then this is the Charles law, and of course the combined gas law. So do not forget this laws because this is important for deriving the thermodynamic processes. So here, the fact number 4 is the first law equation. Okay, so just recall about the law, about this law. So Q is equals to change in internal energy plus work. So this is the heat transferred, this is the internal energy, and then this is the work done. So fact number 5 is about the heat transferred. Okay, so this is based in the first law of thermodynamics, and then we could say the other formula for the heat transferred is mcat, wherein this is mass, this is a specific heat, this is a change in temperature. So the fact number 6 is about a specific heat. So in a specific heat, you will be encountering two specific heat, C sub P and C sub V. So what are these? When we say C sub P, it means a constant specific heat at constant pressure. Okay, so this is a specific heat at constant pressure. When we say C sub V, this is the specific heat at constant volume. So fact number 7, the internal energy. Okay, so the internal energy is also equal to MCAT, wherein you are using a specific heat at constant volume. No matter what happened, whether the volume remains constant or not. So it means that in all processes, the internal energy is this equation. You're going to use this equation. So except when the change in temperature equals to 0, because it is obvious that the internal energy will become 0. Okay, so fact number 8 is about work. So we all know that this is the formula for work. The change in work is equals to pressure times the change in volume, or dW, or the derivative of W, equals P times the derivative of volume. So in other terms, if you're going to derive, if you're going to integrate, so both side integration, so the remaining will be work is equals to the integral of pressure times the derivative of V. So fact number 9 is about the enthalpy. Okay, so enthalpy, so here is the first equation. Enthalpy is equals to the internal energy plus the work. And then the enthalpy, the change in enthalpy is equals to mass times the specific heat at constant pressure, C sub P, times the change in temperature. Okay, whether the pressure remains constant or not. So it means that in all processes, you are going to use this equation, C sub P, except for the change when the change in temperature is equals to 0, because of course it is obvious that the change in enthalpy will equal to 0. So the last fact about this topic is the entropy. So the change in entropy, so this is a change in entropy, is equals to the heat transferred over temperature, or entropy is equals to the integral of heat transferred over the temperature. So do not forget the 10 fact. So the first process that we will be discussing is about the derivation of formulas for isometric process. Okay, so same. So now, okay, when we say isometric process, the change in volume equals to 0, because at this process the volume is held constant. So do not forget this one. So now, the PVT relations of isometric process is applicable using the Gay-Lussac's law. Okay, so using this equation. Now the work is using, so just recall from the 10 facts. So work is equals to the integral of PdV. So this is the formula. And then since the change in volume, or dV, is just equals to 0, that is why the work is equal to 0, or the change in work is equals to 0. So that's how the work equals to 0. Now, the change in internal energy for isometric process. Okay, so using the first law equation, so again recall the change in, Q is equals to a change in internal energy plus work. So since work, or change in work, is equals to 0, so we could say that the the heat transferred is equals to the internal energy. So that is why, and we all know that the heat transferred is equals to m cut. That is why our change in internal energy, which is also equal to the heat transferred, it is equal to m cut mass times C sub V times the change in temperature. So why are we using C sub V? It is because we are in the process at constant volume. That is why use the specific heat at constant volume. Okay. So the heat transferred, so here it is. So Q, or the heat transferred, is equals to mcat. So again, we use this one, C sub V, because we are at constant volume. Next is the change in enthalpy. Okay, so based on the facts that I have discussed earlier, so change in enthalpy is equals to m C sub B change in T. So why are we using C sub B? Since we are at constant volume. It is because no matter what happens, whether it is at constant pressure or not, the change in enthalpy is this equation. Okay, so that is, so next is the entropy at isometric process. So we all know that the entropy is equals to the integral of heat transferred over the temperature. So using the formula for the heat transferred, and we all know that the heat transferred is just equal to mcat, or m times C sub V, specific heat at constant volume, times the change in temperature, and just copy the denominator. So then we are going to transpose the mass and the specific heat at constant volume, and then integrate. So it's just a simple integration. So we're going to use the upper and lower limits, and then so this is the integral of dt over t. So here it is. So since this is the initial condition for temperature, and this is also the final condition for the temperature, excuse me. So if you are going to integrate this equation, we can have this. So mass times the specific heat at constant volume, so open parenthesis, ln of T sub 2 minus ln T sub 1, and then applying the logarithm properties or logarithmic properties, so we can have this equation. So this is where it came from. Okay, so our equation for the entropy is equals to mass times C sub V, or specific heat at constant volume, ln T sub 2 over T sub 1. So this is the equation for the entropy. Now let's talk about the derivation of formulas for isothermal process. Okay, so this is what are we going to derive, or to know where the formulas came from. So again, when we say isothermal process, its basic definition, it says that the change in temperature is equal to 0 because this process occurs at constant temperature. So now the pressure volume temperature relations of isothermal process is applicable using the Boyle's law. So P1 V1 is equals to P2 V2. So next is the work done by this process. So again, we can say we all know that the work is equals to the integral of P dV. So using the ideal gas equation, okay, so PV mRT, and if we're going to derive the equation, we could say that divide both sides by volume. We could say that it is the pressure is equals to mRT over V. So then this equation we are going to substitute here. So P, which is equals to mRT over V, so it is here. And then we are going to transpose the mRT. Okay, so this is constant, right? So we are just going we are involving only the derivative of V. Okay, so it means we are going to have the integral of 1 over V with respect to V, wherein V here is the volume. So again, our volume or the initial conditions, this is the V1, which is the lower limit, and then the V sub 2 is the upper limit. So if we are going to integrate, we can have, so this is constant mRT times ln V sub 2 minus ln V sub 1. And then using the logarithm or logarithmic properties, so we can have m times the ideal gas constant, initial condition for temperature ln the final volume over the initial volume. So this is equation number 1 for the work under isothermal process. And then we all know that using the ideal gas equation PVMRT, right? So we can be able to substitute this one to here, okay? So that's why. So why are we going to put here a subscript 1? So because this is at initial condition. So the same here, this should be at initial condition. So we have two equations. Okay, so now the same here, since we are at Boyle's law, and again we all know that Boyle's law, it is in mathematical equation P1 V1 is equals to P2 V2. So they are just equal. So you just substitute this one. Okay. So the next one is the change in internal energy. Okay. So the change in internal energy is equals to 0. So why? It is because we all know that the change in internal energy is equals to m times, mass times the specific heat at constant volume times the change in temperature. Since we are at isothermal process or at constant temperature, that is why change in temperature equals to 0. So our internal energy or change in internal energy is equals to 0. So the heat transferred of the isothermal process, so from the first law, okay, so heat transferred equals change in internal energy plus work. So since our change in internal energy, so from the previous slide, so it is equal to 0, and so we could say that Q is equal to 0 plus W. So overall, we could say that the heat is directly proportional or it is equal to the work. So here it is. So from the previous slide, or the one that I discussed earlier, the work is equals to, so it is equals to mRT T sub 1. So they are just equal with Q. So just copy. So the same with this one. So for the second equation. Okay, so here it is. So now we all know that at Boyle's law, right? So P1 V1 equals P2 V2, or deriving this equation, we can have, they are just equal. So P sub 1 over P sub 2 is equal to V sub 2 over V sub 1. So using the Boyle's law, you can substitute. So as you can observe for our equation 1, 2, and 3, right? So you can substitute this one, p sub 1 over p sub 2 here, because they are just equal. So it is also possible. So it depends upon the problem. So if the problem it has a final and initial condition, or it talks about the final and initial conditions of the volumes, so you are going to use this equation. But if the problem talks about if the givens are at we have an initial and final conditions for pressure, so just substitute this one in this part. Okay, so that is so easy. So the fifth one, so let's talk about the change in enthalpy of isothermal process. So why the change in enthalpy equals 0? So because the change in enthalpy, so we have again, so it is equal to mass times the specific heat at constant pressure times the change in temperature. So since change in temperature is equals to 0, that is why our change in enthalpy is equals to 0. So now is the entropy. So again, the change in entropy is equals to Q over T, right? And using the equation of heat transferred, okay, so this is the equation for the heat transferred, right? Okay, so this is the heat transferred, copy, and substitute it here. So then the T sub 1, or the temperature at internal initial condition will be cancelled out. So the remaining equation will be here. So change in enthalpy is equals to mass times the ideal gas constant ln final condition for the volume, over initial condition for the volume. So this is our first equation. So applying again Boyle's law. So as a reminder, so here, so just substitute this one in here. So it depends upon the problem, if what is the available givens. So again, we can also have this equation, mr ln p1 over p2, so based from the Boyle's law. So